Welcome to part 3 of the lecture on the static single assignment form. So, to recap a bit, here is an example of the SSA form and the non-SSA form as well. So, the non-SSA form is just a flow graph, whereas in the SSA form some of the join nodes will have Phi functions for the incoming parameters. For example, I in the original flow graph flows from B1 into B2 and also from B7 into B2. So, in B2 in the SSA form we have a Phi function which really takes two parameters I3 and I1. I3 corresponds to the first parameter coming from B7 and I1 corresponds to the second parameter coming from B1. Similarly, the variable n is read here. So, that is like a definition, and later we have definitions of n in B5 and B6 as well. So, in B7 we have a Phi function for n which has two parameters n3 and n4 corresponding to these two predecessors, and then in B2 we have another Phi function for n which takes care of n coming from B1 and this n6 which is coming from B7. So, that is how Phi functions are. So, we also saw how to insert Phi functions, how to rename the parameters of the Phi function, etc. So, we were looking at the optimizations with SSA forms. There are many optimizations which are very fruitful on such forms. For example, dead code elimination, then simple constant propagation, copy propagation, conditional constant propagation, constant folding, global value numbering. These are all optimizations which can be done very effectively on the SSA form. Simple constant propagation is really simple. Take all the statements, put them in a statement pile, and then take one at a time from the statement file. If they are trivial Phi functions with all parameters being equal and a constant, then such statements can be replaced by x equal to c. Otherwise, if there is a statement x equal to c, then we take the du chain of that particular x, and then for all uses of x we can really substitute c, and then the new statement is also added to the statement file, so that we can propagate constants further. Copy propagation is very simple. If there is a single argument function x equal to phi y or a copy statement x equal to y, these can be deleted. We can substitute y for every use of x. This is possible because every definition, every use is reached by exactly one definition in the SSA form. The conditional constant propagation is special. So, let us recapitulate the transfer function of the conditional constant propagation framework. So, this is monotonic, but it is not distributive, and here is the lattice of the constants. So, all the constants are incomparable. There is an undefined value at the top and not a constant value at the bottom. So, how does conditional constant propagation on SSA forms work? So, SSA forms along with extra edges corresponding to the definition use information are used here. So, edge from every definition to each of its uses in the SSA form, hence we call these as SSA edges. So, they are also available in the graph. So, it uses both flow graph edges and the SSA edges and maintains two different work lists. This is a work list based approach, exactly like the simple constant propagation. So, we have a flow pile and an SSA pile. So, it is important that flow graph edges are used to keep track of reachable code. So, whatever code cannot be reached will have at least all the edges incoming into it marked as non-executable, and therefore, we can never reach that node. So, these are SSA edges are helpful in the propagation of values. Whenever there is a change of value in the node, the SSA edge is used to activate that particular node and put it into the SSA pile. So, the flow graph edges are added to the flow pile whenever a branch node is symbolically executed or whenever an assignment node has a single successor. whereas SSA edges coming out of a node are added to the SSA work list whenever there is a change in the value of the assigned variable at the node. So, the algorithm really needs only one lattice cell per variable, not on a per node basis, and 2 lattice cells per node to store expression values. So, not too much of extra space, and then conditional expressions and branch nodes are evaluated, and depending on the value either one of the outgoing edges corresponding to true or false, or both edges corresponding to not a constant are added to the work list. So, if you are able to evaluate it to either true or false, only one edge is added, otherwise both edges have to be added. At any join node, the meet operation considers only those predecessors which are marked executable. So, that is an extra point to be noted here. So, let us look at the algorithm. We saw an example, we will run through that example again a little later. So, G is the SSA graph, N, E F and E S. Okay. So, E F are the flow graph edges, E S are the SSA edges. Now, V is the set of variables used in the SSA graph, that is the program itself. So, we initialize the flow pile with the first edge start to N. So, all the edges which go out of the start node are added to the flow pile, whereas the SSA pile is kept empty. And then for all the edges in the EF set, that is all the flow graph edges, they are made as dot E dot executable equal to false. So, that nothing is marked as true to begin with. Then V dot cell is the cell associated with the variable V. So, we must initialize that also, it is initialized to top, that is the undefined value. Then y dot old val and y dot new val store the lattice values of expressions at a particular node y. So, these need to be initialized as well. So, both y dot old val and y dot new val are initialized to top the undefined value. So, then there is a big loop which goes on until both flow pile and SSA pile become empty. So, the first one is if flow pile not equal to phi, that is flow pile is not empty. What do? We remove an edge from the flow pile. So, if the edge is not marked as executable, that means we are now entering through an edge which is not yet seen before. So, now mark that particular edge as executable, that is executable equal to true for that edge. Now, we check a couple of things. So, is it a phi node? So, if phi present y, so this is true if it is a phi node, then we call the function visit phi y. So, we are going to see some details a little later. So, if it is not a phi node, then it is an ordinary expression node. So, first time visit y is checked, is saying are we visiting it for the first time or are we visiting it second, third time, etc. If it is first time, then visit expression. The point is visit expression is called on y only on the first visit to y through a flow edge. Subsequently, it is called on y only on visit through SSA edges only. So, if first time visit y is false, then we do not visit that expression right now, we are going to visit it later if any values of the parameters in the expression change. So, if flow out degree is 1, that means we have exactly one successor for the node after doing some processing, then we just add that to the flow pile. Then if the edge has already been marked, that is this part. Okay. So, is it first time y, etc., etc., that is where we are. So, now we look at the SSA pile. Alternately, we are going to look at the SSA pile and the flow pile. So, remove an edge from the SSA pile, again check whether it is a phi node, then call visit phi y. If it is already visited, then visit expression again, because we are now coming through the SSA edge. So, nothing wrong with that. The point is if it is not visited already, the node y is not visited already, that means it is not yet reachable through any flow edges, and therefore, we are not going to visit it at all. Unless a node is already visited, we are not going to visit it when we visit through an SSA edge, that because it may not be reachable at all. So, this loop goes on until both piles are empty. Now, let us look at the details. So, phi present y is simple. If y is a phi node, then return true, otherwise return false. So, what does visit phi y do? So, y is a node. So, take y dot new val as undefined value. So, let y dot instruction dot inputs be the number of parameters of the phi instruction at the node y. So, now we are going to take each one of the inputs and then check whether the edge corresponding to that input is executable. Why? We want to actually take the meat of only those parameters whose corresponding edges are marked as executable, otherwise we do not want to touch them. So, let Pi be the ith predecessor of y, I running from 1 to y dot instructions dot inputs. So, if Pi dot y is executable, then take the corresponding input y dot instruction dot inputs I. So, the ith input is taken in A I. Then take y dot new val and meet it with A I dot cell. So, you get the new y dot new val, right, updated value. So, this is done for all the inputs and we leave out those inputs which come through edges not marked as executable. We do not want to touch them. So, it is easy to see that if a node has not been visited at all, not even once, then nothing gets done at the phi node. This loop will run many times, but in an empty fashion, doing nothing. Now, if the new value is less than y dot instruction dot output dot cell, the old value, then that means the value has changed. Remember, we go from undefined to constant to not a constant, that is downwards in the lattice cell, that is why this less than. So, if y dot instruction dot cell equal to y dot new val, so take the new value as the output value and add the outgoing SSA edges to the SSA pile. So, y comma z, where y comma z is in ES. So, all the edges going out of y are added to the SSA pile, because the value has changed now. If the value has not changed, there is nothing to do, you do not add any more edges to the SSA pile. So, already visited is simple, it simply checks the incoming edges of y, and if one of them is marked as executable, then it is already visited, otherwise it is not visited at all. Check incoming edges of y for all E in x y such that x y is in E f. So, y is our node. So, x y is the incoming edge. If E dot executable is true for at least one edge E, then return true, otherwise return false. So, it is a fairly straightforward function. What does first time visit y do? So, exactly one of the edges must be marked as executable and others should not be. So, if E dot executable is true for more than one edge, then return false, otherwise return true. So, but at least one incoming edge will have executable true, because the edge through which the node is entered is marked as executable before calling this function. So, the first time you come to y, it will be one of the edges, incoming edges will be true. So, you will get something as true, but if more than one edge is true, then we are entering for the second time. So, this will be returned as false. So, what does visit expression do? So, it really processes the expression, whether it is an assignment statement or a branch condition. Take the two inputs, input 1 equal to y dot instruction dot inputs 1 and input 2 as y dot instruction dot inputs 2. So, now if I recall the transfer function, if one of the inputs in x plus y, either x or y is not a constant, then the output is also not a constant. So, y dot, so if input 1 dot cell equal to NAC or input 2 dot cell equal to NAC, then y dot new val is NAC, not a constant. Otherwise, So, we have covered the NAC part. If one of them is undefined, input 1 or input 2 is undefined, then y dot new val is undefined. So, if this is also not true, then both are really neither top or bottom values in the lattice. So, we can do some evaluation. Evaluate the expression as per the lattice evaluation rules. So, evaluate y. Okay. So, the expression is evaluated. Then of course, it is easy to modify this to handle instructions with one operand. So, copy instructions are easy to handle. So, if y is an assignment node, then if y dot new val is less than y dot instruction dot output dot cell. So, the new value that we got here by evaluating the expression is less than the old value. So, that means the value has changed. So, remember we always go down in the lattice. So, take the new value as y dot new val, store it in the instruction dot output dot cell of y, and add all the edges going out of y to the SSA pile. So far it is as we did before. But what if it is a branch node? So, if the value has changed, y dot new val is less than y dot old val, then y dot old val is equal to y dot new val. Now, check whether what is the value of the y dot new val. If it is NAC, not a constant, that means both a true and false branches are equally likely. So, we add both branches to the flow pile. If it is evaluated to true, then we add only the true branch edge to the flow pile. In the case of false, we add the false branch edge to the flow pile. So, this is where if the condition has become a constant and has evaluated to either true or false, then we can avoid actually some of the nodes which can be entered through either the true or false edges. So, we actually remove those as dead code finally. So, here is a simple example. So, let us run through the more difficult example, because this is a too simple example which we ran through last time. So, this example, so we start with the first node B1 after start. So, A1, B1, C1 are all initialized. So, now this particular edge actually is the only one coming out of B1. So, we add this edge to the flow pile, and that makes this particular node to be interpreted next. So, what happens here? So, see that B4 comma B1. So, B1 is the only parameter which is defined. This part is not yet marked as executable. So, nothing is coming out of this. Okay. So, only B1 is 1. So, B2 becomes 1, phi B1 is just B1 which is 1. Similarly, phi C1 is C1 is 0. So, C2 becomes 0, and therefore, C2 less than 100 is obviously true, 0 less than 100, and that makes this particular edge to be added to the flow pile, and this is not yet added. It does not mean it will never be added, it may be added little later. So, now we evaluate B2 less than 20. So, that is also true. So, again the true part is true edge is taken, and we come to B5. So, now in node B5, B3 evaluates to 1 and C3 evaluates to 1, both are constants so far. So, this particular edge which is the only successor is taken, we come to B7. So, once we evaluate B7, again this parameter is not yet available, only B3 is available. So, and similarly only C3 is available. When we evaluate B4, it becomes 1 and C4 becomes 1. This edge is added to the flow pile. That means, we come to B2 once more, a second visit. So, second visit, change in the value of C2 to not a constant, but there is no change in the value of B2. Even with this available, B4 is 1, B1 is 1. So, this B2 becomes 1, but in the case of C2, C4 is 1, but C1 is 0. So, Phi function becomes not a constant. So, now this SSJ edge actually activates the node B5, and node B6, both of them. Okay. So, let us take this particular node. So, B3 now evaluates to 1 and C3 becomes not a constant, because C2 plus 1 is the value, C2 is less than 100, which is not known, right. So, at this point we do not know whether C2 is 100 or not, it has been evaluated to bottom. So, we now add actually both edges to the flow pile. Okay. So, this edge and this edge both are added. So, then we actually in this particular B6 there is nothing happening, which has been entered through this particular SSA edge. Okay. So, B6 there is nothing happening, because this particular edge is not marked as executable. Okay. So, now after this we evaluate this B5, C3 becomes not a constant again, B3 is a constant. So, we come we would have already come here through the SS edge, we come here again. So, now evaluate B7. So, when we evaluate B7 a second time, B4 remains as 1, but C4 becomes not a constant. So, there is a change in value. So, that means we need to propagate the value to this through the SSA edge. This goes on the SSA pile. Now, we come to the third visit of B2. There is no change in B2, there is no change in C2. The B2 remains at 1, C2 remains at not a constant value. So, there are no more SSA edges added to the SSA pile. There were no flow pile edges added either. This was evaluated long back and nothing was done for this particular edge. So, finally, we can remove some of these dead edges. This is dead, this is dead. So, this node is removed and then we get a simplified SSA graph. So, here B2 is 1, C2 has not been evaluated. So, it became not a constant. So, it remains as phi of C4 comma C1, and if C2 less than 100 remains as it is. In this case B3 was evaluated to 1, C3 was not a constant. So, it remained as C2 plus 1. Here B4 was evaluated to 1 and C4 was evaluated as phi of C3, which is C3 itself, but no for value as such. But now we can do some copy propagation and removal of code such as B2 equal to 1, B3 equal to 1, B4 equal to 1, and simplify the entire flow graph to a very small one like this. Okay. So, remember see that the B variable is completely gone. So, this was possible because of conditional constant propagation. So, that is the conditional constant propagation algorithm that we saw until now. Now, let us move on to the next optimization known as value numbering. So, we have seen value numbering before. We did this we did the value numbering on basic blocks. So, we used a hash table, we entered expressions into that hash table, and whenever we found another expression with the same value number, we said these expressions are identical. So, the variables were also entered into the table, but not exactly the same table, it was entered into the name table. Now, then we saw value numbering with extended basic blocks. So, and that actually found a few more the common sub expressions and did a few more copy propagations, etc., etc. The reason was the scope of the expressions and so on and so forth were extended. Now, with SSA forms we can do even better. So, this is a global value numbering scheme which is very similar to the scheme with extended basic blocks. Okay. So, but the scope of the tables is over the dominator tree. So, it is not the extended basic block that rules the scope of the tables, but it is the dominator tree. Therefore, more redundancies can be caught. For example, let us where I am going to show you a picture now. In block V8, suppose you had D1 equal to U1 plus V1 as extra, which are equivalent to A1 in the block B1. So, suppose let us take a look at this picture. In block B8 we had D1 equal to U1 plus V1, right. So, we had something here, and A1 equal to U1 plus V1 is here. So, B1 dominates B8. So, we could have, if we had D1 equal to U1 plus V1, we could have used A1 as the value of D1 directly, that was possible. So, with the dominator as the leading theme, the scope of the tables is over the dominator tree, and therefore, we can catch a few more redundancies. We do not need any DU or UD chains, definition use or use definition chains or edges are not needed here. They were needed for the conditional constant propagation, but they are not needed here. Another interesting feature is it uses the reverse post order on the DFS tree. So, what we really do is we take the SSA graph. So, I will show you that also in a minute. This was the SSA graph. So, we do a DFS on this, depth first search on this. So, this is the DFS tree, right. Now, do a post order on this DFS tree. So, we get stop B9, B8, B4, B2, B6, B7, B3, B1 and start, right. Now, take the reverse of this. So, that gives you start B1, B3, B7, B6, B2, B5, B4, B8, B9 and stop. So, start from the start node and use this order on the dominator tree. So, you can see that we do start, then we do B1, then we do B3, okay. Then we do B7, then we do B6, then we do B5, then B4, right, then B8, then finally B9 and then stop. So, all the idea is by the time you actually look at these children, you would have done you would have finished the processing of their dominators, and therefore, the expressions which were defined in these dominators are all available for use in these children. So, that is what really is the basis of this ordering. So, now okay. This ensures that the definitions are processed before use, that is succinctly put. The back edges, they may be present in the SSA graph. Our example does not have a back edge right now, but later I will show you an example with a back edge. So, back edges make the algorithm find fewer equivalences. So, some expressions which we know are equivalent will not be marked as equivalent when there is a back edge. So, this is bad, but there is not much we can do about it. Then the hash table that we use to store expressions is scoped over the dominator tree. So, for example, an assignment A10 equal to U1 plus V1 in block B9, if it is present, okay. This is not present in the example, but suppose it is present. It can use the value of the expression U1 plus V1 of block B1, since B1 is the dominator of B9. So, let me show you that. So, if we had any D1 equal to U1 plus V1, or what was that? That was A10 equal to U1 plus V1 here. B1 is the dominator, it defines U1 plus V1. So, we would have used that directly, okay. So, we need not have defined A10 again, we could have just used A1 in place of A10. This is possible because B1 dominates B9. So, that is how the hash table works. So, if we had not used scoping over the dominator tree, we would not have caught this, okay. So, now recall that each name is unique in an SSA form. So, variable names are not reused in SSA forms at all. Therefore, there is no need to store old entries in the scoped hash table when the processing of a block is completed. So, remember in the recall that in the case of extended basic blocks, we actually had to remove all the new entries and restore the old entries when we went out of scope. Okay. So, when we returned to the parent, we had to remove the new entries which were inserted by the children, and then we had to restore the old entries also. That is not necessary here, because the old entries there corresponded to old definitions of the same variable which were redefined in the new scope. Here that cannot happen. Each name is going to be defined exactly once. So, no more redefinitions. So, just deleting new entries will be enough. No, there is no question of restoring old entries here. So, any copies generated because of common subexpressions can be deleted immediately. So, for example, we will see that A2 equal to U2 plus V2, B1 is U2 plus V2. So, this becomes A2 equal to B1, B1 is the denominator of B2, see. So, this is a copy, we do not have to retain this copy at all. Wherever A2 occurs, we will be able to use B1 directly, we do not have to worry whether there is a conflict of interest or something like that. So, how do we do that? We are actually going to replace the value number of A2 with the value number of B1. So, whenever we want to search for A2, we automatically get B1. So, that is how the copies can be deleted immediately. Copy propagation is carried out during value numbering itself, the way I just now mentioned. So, copy statements generated due to value numbering in the blocks B2, B4, B5, B6, B7, B8 can be deleted. So, we are going to see how the deletion happens. The valnum table stores the SSA name and its value number, and is a global table. It is not scoped over the denominator tree. I will show you the reasons for it very soon. And value numbering transformation retains the dominance property of the SSA form. What is the dominance property? Recall this: every definition dominates all its uses or predecessors of uses in the case of Phi functions. So, the conditional constant propagation did not violate any of this, it actually preserved the dominance property. The value numbering transformation also preserves the dominance property. So, I wanted to show you the picture of the valnum table, that is here. So, hash table entry has expression and it is indexed by expression hash value. So, when we say expression, a Phi function is also an expression. So, along with the value number of the expression, we must also have the parameters of the Phi function. There are many parameters. So, those are also stored, these will be useful later on. There is something called a defining variable that we need to store here. So, the first time that the expression has occurred, and of course, we take that and the variable on the left hand side of that expression is stored here. So, whenever we find expressions equivalent to the expression here, within the scope of course, we can use the defining variable in place of the new variable that we encounter. The valnum table is simple, it stores the variable name, it stores the value number also, it is actually indexed by the name hash value. This constant or not etcetera is stored here, if it is a constant, it is a constant value, and then the replacing variable. So, as I told you, copies need not be kept. So, for each copy for that variable name, we need to have the variable replacing variable as well. So, this is our example that we are going to run through. It has many redundancies. So, u1 plus v1 is defined here, u2 plus v2 is defined here. So, u2 plus v2 is here, again here, there is u3 plus v3, another u3 plus v3, but remember b2 and b3 do not dominate each other, nothing at all. So, for example, see here b2 and b3 are not dominators of each other. So, the u3 plus v3 which is defined here in b2 cannot be reused here. If it was actually defined here like u2 plus v2, it could have been reused, but not now. Now, whatever is defined in B1 can be used in B2, and whatever is defined in B1 and B2 can be used in B4, the reason being B1 and B2 dominate B4. Similarly, whatever is used defined in B1 and B2 can be defined in used in B5. And finally, what about B8? B1 of course dominates B8. So, whatever is here can be used here. B2 dominates B8. So, whatever is here can be used here, but neither B4 nor B5 dominate B8. So, whatever is used here, defined here cannot be used as a common sub expression here, but we must remember that B4 and B5 supply parameters to the phi function here. So, for example, A phi is phi of A4 comma A2, A4 comes from here and A2 comes along this path. So, it would actually come this way, okay. A2 is defined here, but it comes this way. Similarly, B6 gets B2 from here like that and B3 directly, okay. So, the same is true for B5 and B6 and B7, and when we come to B9 we get one parameter from here. So, that is for A7, A5 is defined in B8, so that comes here. A6 is defined in B6, that comes here, and A3 is defined in B3, so it comes via B7. For B7 it is similar, C4 is also similar. So, let us now see why the Val-num table should be unscoped and then run through the example. So, the unscoped Val-num table is really needed for processing phi instructions. So, for example, a phi instruction receives inputs from several variables along different predecessors of a block. These inputs are defined in the immediate predecessors or dominators of the predecessors of the current block. So, this is obviously true because of the dominance property. So, phi gets many variables along its incoming edges, and they could be defined in the immediate predecessors. So, for example, here A4 is defined in the immediate predecessor, but A2 is defined in the dominator, that is upwards, okay. That is what it is saying, are dominators of the predecessors of the current block. They may be defined in general in any block that has a control part of the current block, subject to the dominance property of course. So, for example, while processing block B9, we need A5, A6 and A3. So, let us look at that A5, A6 and A3. I already showed that A5 comes from here, A6 also comes from here, but A3 comes from this point, okay. So, and whereas if you take B7, B6 comes from here, B1 actually comes from all the way from the top, okay, and B5 comes from here. So, in general the variable could come from anywhere subject to the dominance property of course, any one of the dominators. However, each incoming arc corresponds to exactly one parameter of the phi instruction. So, since the parameter can come from any of the dominators or the predecessors, we need an unscoped value number table. It is not possible to use a simple scoped table, we need an unscoped Val-num table for this. So, this is the picture I just now showed you. So, let us run through this particular example and see how exactly value numbering happens. There are more points to be noted as we go along, and we will refine them at the end of the example. Okay. So, the processing order is always given here. So, we are now processing the block B1. So, it has two assignment statements A1 and B1 equal to U1 plus V1 and U2 plus V2. So, U1 plus V1 and U2 plus V2 are entered into the hash table, and then A1 and B1 actually get entered into the Val-num table, no problem at all. Then the next node to be visited is B3. So, A3 is defined here, the same treatment, U3 plus V3 is entered into the hash table and A3 into the Val-num table. Then B7. So, this defines U3 plus V3, which was already defined before. So, because the hash table is scoped over the dominator, B3 dominates B7. So, we find this B5 equal to U3 plus V3 is nothing but defined one already. So, we have B5 equal to A3 as equivalent, B5 equivalent to A3, A3 is right here. Then C3 is U3 plus V3. So, that is also equivalent to A3. So, we delete these two statements because copy propagation can be directly done. We can store in place of B5 and C3 A3 itself, and that value number automatically takes care of these two usages later on. Then we process B6 in that reverse post order. So, here we find A6 as B1. So, U2 plus V2, which is defined here in the dominator scope, and C2 as B1 again. So, that is also defined here, and we can delete these two. Then we process B2. So, here we find A2 as B1, which was defined before, B2 as U3 plus V3, which is not defined before because this is a different dominator scope as such. So, B3 would have already gone out of scope. B2 is a new dominator scope. So, this is retained as it is and entered into the tables, but C1 as U2 plus V2 is already equivalent to B1. C1 is equivalent to B1 because U2 plus V2 is already defined. Then we come to B5. Here we find U2 plus B2, B3 is equivalent to B1. So, this is deleted. Here in B4, A4 is equivalent to B1. So, this is also deleted. Then we come to B8. So, in B8, A5 A5 has a Phi function with A4 and A2 as parameters. If you trace back, when you search the Valnum table, A4 is equivalent to B1. So, that is what we have replaced here, and A2 is equivalent to B1 again. So, the second parameter is also B1. So, such Phi functions which have all parameters as equal, the same, are meaningless Phi functions. So, A5 is a meaningless Phi function, we do not need it here. We can simply replace the Phi function by the parameter B1. So, A5 is equal to B1, but B1 is already there before. So, this is a copy statement and therefore, we can delete this as well. But B6 is not so, B6 is remains as Phi of B2 comma B1. When we come to B9, A7 is a Phi function with A5, A6 and A3 as parameters. So, A5 is same as B1. So, the first parameter is B1. A6 is same as B1, second parameter is also B1. A3 is A3, there is no change. So, it remains as it is, the Phi function does not become meaningless. The second Phi function B7 has B6, B1 and B5 as 3 parameters. So, B6 is as it is, B1 is as it is, and B5 is equivalent to A3. So, it is replaced by A3. So, this Phi function is also not meaningless, it remains as it is. Whereas, C4 equal to Phi of C1 comma C2 comma C3, C1, C2, C3 are equivalent to B1, B1 and A3. C1 is B1 here, C2 is B1 and C3 is A3. So, now observe that A7 and C4 are exactly identical. So, therefore, one of these needs to be retained and other can be removed. C4 will be removed and it is called as a redundant Phi function, which is already covered by some other Phi function in the same basic block. So, this is the simplified SSA graph after the copy statements and redundant expressions etc. are all removed. So, this is how we are able to simplify. Now, let us look at the SSA value numbering algorithm in a formal manner. Mark the beginning of a new scope. So, the basic block B is the parameter. For each Phi function f of the form x equal to Phi of y1 to yn in the basic block B, do search for the function f, the name f in the function f in the hash table, name is x and the parameters are y1 to yn. So, this involves getting the value numbers of the parameters. So, you have to dig into val num tables, get their parameters, etc., etc. Then use a special hashing function for phi, and there are any number of them available, and then enter into the hash table. Suppose you find that f is meaningless, this will be defined later, all yi are equivalent to some w. So, that is all the parameters are equal. Okay. Now, replace the value number of x by that of w, because this becomes x equal to w, okay. All these are w in the val num table and delete f. Suppose it is not meaningless, but it is redundant. So, redundancy is there is some other phi function which is equivalent to this f of the form z equal to phi of u1 to un in the same basic block. So, replace the value number of x by that of z in the val num table and delete f. So, I already showed you this. Otherwise, insert simplified f into hash table and the val number table. Then this is for phi function. What do you do for assignments? If it is x equal to y plus z, search for y plus z, that implies take the value numbers of y, z, etc., etc., apply a hash function and search a hash table. If it is already present with value number n, then replace the value number of x by n in the val num table and delete a. I showed this. So, if there is an expression already defined, we do not have to keep the copy later. Otherwise, add the simplified y plus z to the hash table and x to the val num table. So, this is as before. Now, for each child, now we have finished processing B. So, what about the children of B in the dominator tree? In the reverse post order of DFS, as I told you in about the SSA graph, call SSO value numbering for each of the children. Finally, once we want to get out of B, clean up the hash table after leaving this particular scope. So, initially we start we supply srot as the parameter and then call the function. So, let us look at some details of how phi functions are processed. One or more inputs of the phi function may not yet be defined. For example, they may reach through a back edge of a loop. So, such entries will not be found in the val num table. So, let me show you an example. So, this B3 has been replaced by a new block which has U6 and U7 as new definitions. The old one had only A3 equal to U3 plus V3. So, now U6 is phi of B1 comma A7 and U7 is phi of B1 comma C4. Unfortunately, we found that A7 and C4, even though are equivalent, we have not processed this block. So, we have not found that A7 and C4 are equivalent. We are processing this block, we have not processed this block, and there is a back edge here. So, because of that, we do not find U6 and U7 as equivalent, they are not redundant phi functions at all, because A7 and C4 are not yet found as equivalent. So, because of this back edge, A7 and C4 will be treated as distinct, separate, and therefore, this U6 and U7 will be actually entered into the hash table as if they are two different phi functions which are not equivalent to each other. So, simply assign a new value number to the phi instruction and record it in the val num table and the hash table along with the new value number and the defining variable. That is what we do. So, we do not really go through the value numbering scheme again and again. So, that is why this is not done. Okay. We just want to do it once, it takes too much time. If all the inputs are found in the val num table, then replace the inputs by the respective entries in the val num table. Check whether the phi function is either meaningless or redundant. If neither, enter the simplified function into the tables. Now, what about meaningless and redundant phi functions? All inputs are identical. So, for example, in block B9, B8 as I showed you. So, if all the inputs are equal, then they can be deleted. This particular instruction can be deleted. Occurrence of this defining variable can be replaced by the input parameter. only val num table needs to be updated. So, we saw this example already. So, for example, here this and this they become meaningless, therefore, both these parameters become equal. Okay. Redundant Phi instruction means we have already discussed this instructions in the same basic block with exactly the same parameters. So, redundant Phi instruction can be deleted and all occurrences of the defining variable in the redundant instruction can be replaced by the earlier non-redundant one, tables are updated. So, this is how value numbering actually happens in SSA forms. Okay. So, now let us look at something somewhat interesting. We saw value numbering on SSA graphs, which actually preserved the dominance property. Now, we will see how important it is for liveness analysis. What is liveness? For each liveness is whether a variable is going to be used at a particular sometime later, that is informally what liveness of a variable really is. So, for a variable which is defined, is there any use later on? So, how do you find it in the SSA graph? It is very simple. For each variable v, walk backwards from each use of v, stopping when the walk reaches the definition of v. So, collect the block numbers on the way and the variable v is live at the entry or exit, one or both as the case may be of each of these blocks. So, let me show you a simple example. So, here is our original flow graph and here is our SSA flow graph. So, we really let us look at some usage. Okay. Let us say I2, okay. I2 is used here, I2 is used here also. So, now we want to find out all the blocks where I2 is live. So, let us take this, it is very simple. So, we go backwards till the definition of I. So, we go up to this point, I2 is defined here, right. So, from here to here. So, in block B4 it is actually live, at the entry of block B4 it is live, but the end of block B4 it is not, because there are no more usages here. And at the output of block B2 it is live, and at the entry of block B2 it is not live, okay, because I2 is defined immediately. So, B4 in and B2 out are collected. Then we start here. So, B7 in is collected, then B5 out is collected, B5 in is collected, B3 out is collected, B3 in is collected, and then B2 out is already there, and finally, we have reached the definition point of I2. So, all these blocks are deemed as live blocks for I2. We can do the same thing in along the other path also. From here B7 in, B6 out, B6 in, then B3 onwards we have already collected. So, B2 out, B3 both in and out, B4 only in, B5, B6 both in and out, and finally, B7 in. These are the points where I2 is live. What about N2? So, you can look at N2 which is here, which is used here also. So, from for N2 you go on, it is defined here. So, B5 in, B3 out, B3 in and B2 out. Similarly, here B6 in and then onwards we have already collected, right. So, whereas if you look at N3 or N4, we start N3 is defined right here. So, only this much, N4 is defined right here. So, only this much. Okay. So, this is how the liveness is computed. We just go walk backwards from each use of V, stopping when the walk reaches the definition of V. Collect the basic block numbers on the way, and the variable V is live at the entry and exit one or both of these basic blocks. So, I already showed you this particular example. This procedure works. Why? It works because the SSA forms and the transformations we have discussed satisfy or preserve the dominance property. So, again we must recall that the dominance property is definition of a variable dominates each use or the predecessor of the use when the use is in a phi function. Suppose the dominance property was not satisfied, then there is a problem. What may happen is that the whole SSA graph may have to be searched. We do not know, dominance property is not satisfied. Here we are 100% certain that if we reach the definition, that is sufficient, because the definition dominates all the uses, okay, or at least the predecessors of the uses. So, because of that we stop at the definition, we do not have to go beyond that. Whereas, if the dominance property is not true, then the definition could be anywhere, it is not necessarily up to the dominator only. Okay. So, the whole SSA graph may have to be searched and to find the corresponding definition. So, this is a sample of how liveness analysis is possible. It is also possible to actually do partial redundancy elimination and a few others, but they are much more complex than what I have presented so far. So, and those are outside the scope of this particular course. So, this is the end of the lecture, and in the next time we will look at parallelization. Thank you.